No, I think.
Okay, so let's get started. There is a little announcement. We have realized that having the poster review at the end of the session is not such a great idea because you're advertising posters that you should be able to look at during the coffee break, but the coffee break is already passed. So unless you have time travel, it's hard to make it work. So we will try to make this a little bit better, and so the poster review will schedule just before the coffee break. So you have an idea of what the posters are there, and then you can visit the posters in the coffee break. It's much more rational. Thank you, Claudia, for pointing that out. And so we'll start with this session. We have just a point swap between the talk of LHCb just before the coffee break and the poster review, and they are swapped. And we'll update the program as soon as possible. We'll try to do also for the other sessions. I will communicate with the speakers so that they are not too surprised. And now, without further ado, let's start the session. Please, Claudia.
Okay. Welcome, everybody. So, and indeed, we start promptly with Lena from Freiburg that will tell us about timing resolution for Elgats and 3D sensor. So.
Okay. Yeah. Thank you. I will tell just a bit about the measurements we are doing in Freiburg about time resolution studies. And just a small introduction, the Future Hadron Colliders challenge the silicon sensors regarding tracking and reconstruction with very high range and a huge pileup. And Atlas and CMS already aim for 30 to 40 picosecond time resolution. And future checkers like the FCC HH will demand timing of 5 picoseconds while still providing a good position resolution below 10 micrometers in the high density environments. So we need faster sensors which still provide very good resolution. The high radiation doses, of course, challenge the sensors additionally. And as silicon sensors have been proven radiation hard and have a very short charge collection time, they are the current and the future choice for most of the tracking detectors. And we have many collaborations working on improving the time resolution, e.g. on ultra-fast silicon sensors, which are mostly Elgats, but also 3D pixel sensors, which are dedicated then for timing. Just a few words about the sensors that we measured. We had some low-gain avalanche diodes, which have an avalanche region to create fast and high signals by charge multiplication. We tested some Elgats with different gain layer dopings. They all had an active thickness of 50 micrometers and an area of only 1.3 times 1.3 square millimeter. And they were produced by Hamamatsu for the more inside people in the HPK Run 2. The 3D sensors that we have, they have the junction and the ohmic columns etched into the sensor so that we have very short drift distances for the particles. We tested strip and pixel sensors with both an active thickness of 235 micrometers. And the columns are etched in so that there's only 20 microns of no junction or ohmic column left. The strips have a unit cell size of 80 times 80 micrometer squared, and the pixels only 50 by 50. They were produced by CNM. These are not dedicated timing sensors yet, but just were sensors which were basically left from other production runs, which we could use for testing them regarding timing. The setups we use for testing the time resolution is one setup using a strontium-90 source to create MIP-like electrons, and we have a Elgat with a very well known time resolution as a reference sensor, and we have a scintillator photomultiplier combination below the DOT to have a yes-no trigger, so that we definitely have MIP-like electrons only. And then we record approximately 3,000 events with the DOT signature to have appropriate statistics, and if possible we trigger only on the reference sensor and on the scintillator to have no bias on the sensor at all. For the very small pixel sensors, this is not always possible, so we had to add a third trigger on the DOT. The second setup that we use is the laser setup, where we have a laser pointing on the top of the sensor, creating charges throughout the entire sensor. It's an infrared laser. We record 2 pulses, which were split by a fiber splitter with a 25 nanosecond distance, so that we have also 2 pulses we can use for the timing analysis. And the intensity of the laser, of course, is tunable, and we always try to achieve approximately the equivalent of 1 MIP. But for the 3D sensors, this is more difficult, as they have a very non-uniform electric field. So I start with the time resolution of the Elgats that we had in the setup using a MIP-like electrons. We have 4 different splits, with a very high gain layer doping to a very low gain layer doping. So split 1 is the highest and split 4 is the lowest. And as you can see, for the high gain layer doping, we need a much lower voltage to have the avalanche effect kicking in, while for the lowest gain layer doping it takes a longer time, but for the lower gain layer dopings we reach in total the better resolution, because the overall electric field in those sensor bulk is higher as well. The irradiated sensors are shown in the right plot, which are measured now at minus 18.5 degrees, along with one sensor which was not irradiated but also from split 2, to have a comparison. And as you can see, with increasing fluence we need to increase the voltage significantly as well, but up to a fluence of 1.5 times 10 to the 15 we still achieve approximately 30 picosecond time resolution. So the sensors definitely survive fluences until 1 times 10 to the 15, but we have to provide a much larger bias voltage. Now comparing these results with the TCT measurements. With the TCT we don't have Landau fluctuations because we're creating the charges with the laser, so we have in total a significantly smaller time walk contribution, therefore a better time resolution. And the jitter is the most important contribution to the resolution we are measuring here. You can see that for the unradiated sensors we reach down to 10 picosecond timing for the split 2. And compared to the timing setup, we have a much steeper slope for the time resolutions for the unradiated ones as well as for the irradiated ones. And for the irradiated ones, you can see there's directly compared the beta measurements with the TCT measurements, that the slope of the increase of the time resolution is getting smaller with higher irradiation doses. So it's getting more like the the beta measurements, which is we think because we have in the laser setup no gain layer suppression because we use a very broad laser beam, and in the beta setup we have point-like particles. This gain layer suppression has an effect, which is also what we saw in the signal, where the signal was increasing much stronger for the TCT setup with the voltage than for the timing setup. This is kind of an interesting comparison to do without the gain layer suppression in the laser setup. Then I come to the 3D pixel sensors. Before irradiation, we measured them in the timing setup, and we sent them to irradiation and got them back, so these are really the exact same sensors. Before irradiation, they achieved 30 to 31 picosecond at room temperature, and after irradiation, we had one irradiated to 1 times 10 to the 15 and one to 5 times 10 to the 15 even. And as you can see, the performance after irradiation is very good. We reached 26.7 picoseconds for 1 times 10 to the 15 and even 24.5 picoseconds for 5 times 10 to the 15. And if you look at the signal plot, we can see we first have for the 1 times 10 to the 15 sensor a smaller charge measured, which is of course expected because we have losses due to the trapping. But for 5 times 10 to the 15, the charge is increasing significantly, so we have charge multiplication. At least that's a hint to that, and also that we achieve the best time resolution for the 5 times 10 to the 15 sensors hints to that, because of course we have a very fast signal then if multiplication sets in. Looking at some other values regarding the timing here for the 3D sensors, the rise time kind of confirms the theory of charge multiplication. as well as the noise plot. So we have a lower rise time for the 5 times 10 to the 15 sensors than all the other sensors, and a higher, but also a higher noise. The noise for the 1 times 10 to the 15 sensors is lower than the unirradiated ones, but this is only because we're measuring these sensors now cold. So of course the noise is a bit suppressed because the leakage current is lower. So in total, the sensors perform very well after irradiation, and especially comparing this now to the Elgats, we can see for the 3D sensors, we don't need a higher voltage after irradiation. We can still bias them with the same voltages and achieve the same or even a better time resolution. The Elgats are radiation hard, but we need a much higher voltage. And comparing the rise time especially, the 3D sensors perform much better. What has to be noted here is we're not using the state-of-the-art Elgats, so there are faster Elgats than this. So there has been a lot of development since this production run, but yeah, these measurements really show that the 3D sensors are competitive with the Elgats and are an interesting topic to investigate for timing sensors as well. For the 3D sensors, the TCT measurements, of course, are interesting as well because we can measure the position-dependent time resolution. So we measured for the pixel sensors, unradiated first, an area of 10 times 40 microns in 5 micrometer steps. You can see the area that we measured on the bottom left. And the plots for the two sensors, the time resolution plots are then shown on the right. And for both, you can see between two junction columns, the electric field is much smaller. So we have also a worse time resolution. Well, the best time resolution we achieve between junction column and ohmic column. And the range of 23 to 43 or 25 to 47 picoseconds is also agreeing with the timing measurements, but of course there's a large range depending on where we measure. If we are shooting at a very low field spot, we of course have a much worse resolution. The differences between these two plots are of course position uncertainties, the laser focus and the laser intensity, which have a large influence on this measurement, but just to show that we can correlate basically the electric field with the time resolution. These plots are very nice to show. You can see this as well in the MPV and in the rise time, of course. In the MPV, it's not as pronounced in the as for the time resolution. We have a higher MPV the closer we are to the readout column. But we don't see as much the field distribution for the rise time. It's much stronger again, but there we also have a very direct correlation between the electric field and the slope of the pulse, which is determining the rise time for us. Then, because there we have a much larger area to measure, we measured as well a 3D strip sensor, where we have measured two areas of a total of 4 unit cells. We measured this as well in the beta setup for comparison, so there we achieve about 75 picoseconds, which is of course much worse than the pixel sensors, but the capacitance of the sensors is of course much higher when we have the strips, and the unit cell size, the strip pitch, is also much larger, so it's expected that we have a worse resolution here. But now, looking at the TCT measurements, we can very clearly see the cell structure. So I sketched the strips we have and the ohmic columns in the middle of the strips, and you can clearly see where the low electric field is between two junction columns, and also around the ohmic column where the laser is not penetrating very deep into the sensor, where we have a much worse time resolution. Between the junction column and the ohmic column, we achieve the best time resolutions because there the field is the strongest. And so these measurements really directly correlate to the expectations we have from the electric field in the 3D sensor, which we saw in simulations. And the resolution here measured is between 65 and 83 picosecond, which is also agreeing very well with the beta measurements. Looking as well as the jitter and the rise time, we see a different, similar pattern of the cell structure. Of course, there are some differences. It's always, with some fluctuations, but still you can see clearly this, the cell structure, and this confirms the correlation there. The rise time in the TCT measurements is much higher than in the beta setup, but this is corresponding to the laser there. And the jitter was higher as well because we had a little bit higher signals than in the higher noise than in the beta setup. Then to come to a conclusion, The time resolution of silicon sensors is a very important research topic right now for the upcoming and also the future detectors. And before irradiation, for these Elgats and 3D sensors we measured, we have a very similar time resolution of 30 to 35 picoseconds. After irradiation, the Elgats need a significantly higher bias voltage, but still are working and achieve the same time resolution, while the 3D pixel sensors even improve after irradiation because of the set-in of charge multiplication, and the bias voltage range stays the same. We don't need to put higher voltages. Because of this very small distance that needs to be depleted, the depletion voltage is still below or around 20 volts only. And the position-dependent time resolution measurements correlates very well with the electric field, so kind of confirms the expectations there very well. And just as a short outlook, we will test also higher irradiation doses of different 3D and also different 3D sensor geometries to see how the geometry is influencing the time resolution. We have, for example, 25 by 100 micrometer pixel sensors. And there is a dedicated 3D timing project where there will be also completely different geometries, like the hexagonal geometry tested, where simulations show that there are even better time resolutions expected than for these sensors, which were basically just sensors we had left from a different production run. So thank you for your attention.
Thank you, Lena, for the very nice talk. I would open. Okay, I see a question. Can you tell us your name? So for everybody also, there is.
Huh? Sorry, you need to...
Can you tell us your name? So
yes, it's Mengqing here. It's a very nice talk, very interesting to follow. I have one question. It's very nice actually to see that, as expected, the time resolution along the geometry of the 3D sensor follows the magnetic field as expected. But my question is that, what is your expectation to really make use of it as really for timing measurement into a detector, towards a detector, because of this inhomogeneous distribution of timing resolution?
I mean, with this, knowing that this is directly corresponding to the electric field, we know that we have to design the sensors in a way that we avoid these zero electric field spots that we have in this square geometry, which is one example why we go for the hexagonal geometry. Of course, this is just like a nice proof, but in the end, the measurement that counts more because it's more close to the real-life scenario are the better measurements, and they show as well that this is kind of like an average of all the time resolutions we measure in the TCT. So the important measurements for like a final time resolution are definitely the better measurements to have a comparison to the real life scenario.
I think we have a question there. And then here.
These measurements are still on very small samples of detectors. So 2 questions. What can you say about the variation that you see between one kind of sample of the same kind of detector and another? And do the results depend very much on the environment, such as temperature? And the second thing is, you mentioned a couple of times state-of-the-art developments. What do you mean by that? What things are you changing to optimize the performance?
So the first question, we measured different samples of the sensors. I didn't show all of the results that we have. And for example, for the 50 by 50 pixel sensors, we had a variation of maybe 2 picoseconds in the time resolution we achieved for different samples. And also these measurements, we just call them one sensor, but on each structure we have up to 16 pixel sensors we measured. So we can have a bit of statistics on how they really behave, and we didn't see a large spread there. they are not as dependent on the temperature as the Elgats, for example, because we don't, especially for the unradiated ones, we don't have an avalanche effect. Of course, there is a small temperature dependency because the velocity of the particles is always playing a role, but it's not as significant for the Elgats. And for the Elgats, I mean, there are many new developments. I'm not an expert in that field, but I know that there were a lot of improvements on for example, adding junction termination extensions to the sensor and increasing the fill factor, changing the how the gain layer is doped and so on, in order to improve the sensors. But I'm not an expert in Elgats, so I cannot really answer. I just know that there definitely are sensors which achieve already below 30 picoseconds timing regularly.
Okay, we take a quick one by Norbert.
Yes, your result that the gain does obviously not depend on the irradiation, suggests that the gain layer actually is not really eventually not important. But it would be interesting to see, because for unirradiated signals, the holes moving back from the gain layer to the other side make the large slew rate. Now, if you change that and you basically get the timing from, it would be interesting to see whether the electrons are now determining in the signal the timing of the arrival. You know what I mean? Okay.
I'm not 100% sure, to be honest. But
Okay, we talk about it.
Yeah,
Yes,
maybe we take, okay, you take offline. Thank you, Norbert, for the comment. And we move on to the next speaker. We thank again Elena for the very nice talk. And yes, next is Laura from Birmingham.
Ok, non ho nessuna tasca. Ok, così lo metto. Se riesco.
So Laura. Okay, Laura Gonella from Birmingham will tell us about the upgrade of the Atlas detector and its tracking system for iLumi.
Okay. Right, thank you. So my talk today is an overview of the Atlas ITK detector system for the phase 2 LHC upgrade. So this phase is also known as the high luminosity LHC phase because the machine luminosity will increase up to a factor 7.5 above the nominal LHC luminosity. So this will allow the experiment to collect an integrated data set of up to 4,000 inverse femtobarn. So this is 10 times higher than what experiments are collecting during the LHC run. And this will happen on a 10-year time scale starting in 2029. So what this implies for the tracking detector is represented graphically here in these pictures. So basically it means we have a lot more tracks to reconstruct. So the current Atlas inner detector works very well in this environment here at the LHC, where we expect up to 55 pileup events per bunch crossing. However, when we go to the iLumi LHC and we go up to 200 pileup events, the current Atlas inner detector cannot cope with this environment, so we have designed and we are building a completely new inner tracking system that is made of silicon pixel and strips. So one of the overarching goal in designing the ITK was that it not only had to meet the challenges of the iLumi LHC, but also doing it while maintaining or maybe improving even upon the resolution of the current Atlas inner detector. So to deal with the instantaneous condition of high pileup and event rate and occupancy, we have developed sensors that have much higher granularity than the ones that are currently used. ASICs that have a faster readout and are more robust against single event effects. And then we have also tried to increase the number of layers so that we have enough points for pattern recognition. The other important point was the effect of the integrated luminosity, which means a lot of radiation does deliver to the detectors during operation. So all of this technology also had to be made radiation hard to levels that were not experienced before, so up to fluencies of 10 to the 16 neutron equivalents per square centimeter and 10 megagray total ionizing dose. So this is just a rendering of how this detector will look like when we finish building it. So there is a pixel detector close to the beam pipe surrounded by strip detectors. And we always have cylindrical layers around the beam pipe. We call this the barrel region, and then discs at the two sides, and these are called end caps. So the table here show you some numbers from this detector. So it's almost 180 square meters. It's going to have up to 27,000 modules and almost 6 billion channels. So what you also see here in gray, these are the numbers from the current inner detector pixel and strip system. So you see that this ITK is not just bigger, but it also has a much higher granularity. What the ITK also does more than the current inner detector is that it has a coverage up to a pseudo rapidity of 4 from 2.5 that it is right now. And this was achieved with some very new design of the support structures that allow to have in the pixel region some inclined modules, and also with a very novel ring structure here. So here in red are the pixel layers and disks. And then this detector will also provide at least 9 points per track. And this is achieved by complementing this 5 layer of pixel with 4 barrel layers of strips and 6 disks of strips per end cap. Now, despite this detector is much larger and with more channels to service with respect to the current inner detector, it has a lower material budget, especially at very high eta. And this was achieved with a lot of work to build more light wave cooling system and support structures, but also with new readout schemes, and also some very also new innovative powering scheme, especially for the pixel, where they use a current-based one, serial powering. So what I'm showing you here is just a few plots on the expected tracking performance. So in red is the performance expected at the iLumi LHC. This is tracking efficiencies versus eta and versus PT. So in red is the performance of the ITK with 200 events pileup, and in black is the current Atlas inner detector with 38 pileup. So despite the increased pileup, we maintain the resolution in the barrel region, even a bit improved, but then we extend it further at high eta with efficiency over 85%. So this is all I'm going to show on performance, because there are two posters that you can look at on tracking and reconstruction performance, also readout. There are also two posters on general ITK detector operation and safety. So I will now move and describe a little bit the strips and pixel systems. So for the strip detector, I don't think this microphone is placed very well. It sounds very noisy to me. It's okay? Okay. Okay. So for the strip detector, we have modules that are the basic building blocks. So these are mounted on local support structures. We call them staves for the barrel region and petas for the end cap. The modules are loaded on two sides with a small stereo angle in between, so that they give a 2D measurements. And then staves and petas are assembled on global mechanics, we call, larger structures to form cylinders that then will go into the barrel region, and rings for the end cap. So as I said, the modules are the basic building block, the active elements of the detector, and they come in different flavors depending on the sensor geometry that is different for the barrel and the end caps, and also within barrel and end caps there are variations. However, they all have a very common modular design. So there is a sensor, and then there are two circuits, an hybrid and a power board glued on it. So the hybrid hosts all the strip readout chips, the ABC stars, and then an aggregator controller chip, the ACC star. And the power board, as the name says, deals with power distribution, so both the bias to the sensor and the low voltage to the ASICs. And it also has a monitor and control chip, the AMAC. So there are three ASICs that have been developed specifically for this project. And all the electrical interconnections are done then on the module via wire bonding. So there are plenty of results on sensor and on the ASICs. So in this conference, there are 4 posters that show very detailed characterization of all aspects of the sensor. So because of time here, I show only one result, but this is a key result that we have obtained recently. So what you see here, these are results from a test beam of a pre-production barrel module, where both the sensor and all the 3 ASICs had been irradiated to end-of-life dose at the LHC. So, and you have the efficiency and the noise occupancy, and you can see there is a clear window of operation at iLumi LHC end-of-life dose, where we have both 99% efficiency and less than 0.1% noise. So this is a very good result because it demonstrates that we developed the technologies that can do the tracking until the end of the iLumi LHC run. So it is a great result, but it's far from being the end of our job, because now we need to demonstrate that we can build about 20,000 of these modules over 3 years. And in addition to building them, there is quite an extensive quality control and quality assurance process going on. So this is going to be a global effort. We are going to have about 30 assembly and testing sites for the production of the STRIPS detector. And what you see here on the top, it's a diagram that shows you the part flow between institutes that build the NCAP modules. As you see, this whole exercise involves also quite some logistics in shipping parts around the world. And this is just a top-level diagram. I mean, if you would then look, we have similar one for distributing sensor parts for QC and QA and for the hybrids and so on. So to demonstrate that we can build all these modules in the required time, we are doing 2 exercises. One is site qualification, one is pre-production. So in site qualification, all the sites develop all the procedures for assembling, but also shipping, storing, interaction with the database, and so on. That's about 72% completed now. And then we are doing pre-production, where we build about 1,000 modules as they would be production module, to demonstrate we are ready for full production. And we are almost through the first part, in which we are using pre-production sensor and ABC star. The rest is still prototype parts. And then PPB modules with all pre-production parts is starting. So what you see here, this is a plot of the noise from more than 100 barrel hybrids. And what we get is what we expected from the latest prototypes. And here you see some pictures of first pre-production B modules and hybrids. So finally, for the strips, some words on the local support structures. These are carbon fiber composite with integrated electrical and cooling interfaces, and they are now starting pre-production as well of these ones, and we have a first pre-production A barrel stave with pre-production modules loading on it, which shows, again, very noise performance at different temperatures, and this is reported in a poster that you can also see. Global mechanics are ahead of the game. They are already in production. So let's come to the pixel detector. So similar concept, modules loaded on local supports. However, here there are a lot more varieties in local supports because you need the structures that allow to mount the modules flat or inclined. So there are different structures for the outer barrel, for the outer end cap, and for the inner pixel system. And here I would like to remind you the inner pixel system is very close to the beam pipe, only 3.4 centimeters away, and it will be replaced halfway through the iLumi LHC for radiation harness. For the modules, there are 2 main types, quad and triplet. They are made with different sensor, and within each there are variation in pixel size and sensor thickness to fit the needs of the various regions in this detector. So I would like to spend just some time to say a few words on the 3D sensor, because these are really the technology that enables to be so close to the beam pipe. So these are now developed with a new single-side technology that makes the process simpler, so it improves yield and production. So they have a very thin substrate and small pixels, so cluster size is reduced. They can better handle data rates and for improved impact parameter resolution. And here you see the efficiency maps from prototypes. So you see that they reach an efficiency above 96% at 1.6 10 to the 16 neutron equivalents per square centimeter, and this is with a very small bias. And now these sensors are in pre-production. Another key innovation for this detector was the readout electronics. This is a new front-end ASICs in 65 nanometers, so that was the first sign that this technology has been used. It's a common Atlas and CMS R&D. There has been a large-scale prototype that has been used by the ITK Pixel for a very large prototyping programs, and now the full-size chips has been developed, so it's radiation hard to up to 5 megagray. It can handle very high heat rate. It has integrated design of regulators for serial powering, data formatting, command forwarding. So it's now also in pre-production, and the production version it's going to be submitted in June. Yeah. Okay, so and then just a few words on module. Also for this there is a poster that details all the steps to build this module. So here sensor and ASICs are bonded and then connected to flex circuits. They also do here parilene protection. This is to reinforce the bond and prevent corrosion and also discharge between sensor and ASICs. As I said, the quads are made of one sensor with 4 ASICs bonded. The triplets in reality are 3 single chip modules sharing one flex. So there has been more than 200 module prototypes built with the RD53A prototype, and now the first few modules are coming available with the full-size readout chip. Pre-production will start later this year, and module production starts then at the end of 2023. And here it's going to be about 9,000 modules to be produced in 2 years by 20 assembly sites. Okay, so I come then also here to demonstrators, so also for the pixels. There are large support structures that are being loaded with modules. So the demonstrator program started using modules from the current inner detector, and now they are moving to the RD53A modules. So there are both chains of modules in serial powering, but also then already support structures that are loaded. In particular, the inner system rings and staves are now partially loading. There is testing ongoing. What you see here, it's for 8 quad modules, the variation in threshold when operated with serial powering or direct powering. And John can tell you more about this in his poster. So I come to the conclusion. So Atlas is developing a new tracking system for the high luminosity LHC to cope with the increased particle multiplicity and radiation level. And this detector will provide large acceptance with a large number of points per track, high granularity and radiation hardened, but with minimized material budget. Both strips and pixel detector demonstrated the required functionality for tracking until end of life dose at the high lumi. And now the strip system is progressing to pre-production, and we are going to start production end of this year. Some parts are already in production, and Pixel is finalizing a very extensive prototyping phase, and pre-production of some components is ongoing.
Thank you, Laura, very much. For the nice summary, questions from the floor? There is one.
Hello.
Yep.
So, in your threshold versus efficiency plot, in very lower threshold, you have shown the efficiency is very high. It is greater than 1. So, can you explain a little bit why this is so, and how do you measure the efficiency?
Sorry, what plot was it? Can we go back to the
threshold
slides?
Threshold versus efficiency.
The strip module.
The strip one, yeah.
I think it, yeah, this one.
No, I mean, here you need to look. So you have the efficiency and the noise occupancy. So the efficiency is not above 1. We are plotting two things here.
Okay. And how do you measure the efficiency?
How do you?
How do you measure the efficiency?
The efficiency. Okay, this is measured with a telescope. So we know, we reconstruct the tracks, and then we see the track in the sensor.
Okay, yeah. Thank you.
It's just a standard test beam setup, I think. Yeah. There's a question here, I think.
No, sure, it's for you, but going up to 4 in ITA, it's a lot of effort for ITK. Is it worth it? That
yes.
is no. It's for us, for Atlas.
Yes, exactly. Then I delegate to the project leader. Yes, it is.
I mean, the effort, honestly, So I'm not sure the effort is going up to Forita, honestly. It's more building 5 layers. So in some sense, it complements the physics program. It extends the physics program. Then honestly, it's not the worst, let's say, case, or the worst nightmare, let's say. So really, because at the end, you have several small disks, but I mean, it's not really a huge impact on the project. Otherwise, we would maybe revise our decision, but that's not the criticality of the project. Okay, if there are no any other questions, then we move. Thank you, Laura, again. And we move to the similar talk and CMS perspective by Alessandro Rossi. So I think you share.
Okay. Good morning, everybody. I will discuss about the update for the tracker for CMS, so quite similar argument. So already give a nice introduction to the motivation that, let's say, bring us to the update of the tracking system, the two experiments. So for the iLumi phase, the requirements, and why we need to change almost everything. We need more granularity. We need, above all, to reduce the material in the tracker. This is obviously independent to the luminosity phase. It's always better to have small material inside the tracking volume. But the most important things is that the radiation tolerance of the detector should be much higher with respect to what we have now. So why change everything? Essentially, because what we have now will essentially reach the end of life. Hello? Okay, now it's working. We reach the end of life at the end of run 3, so we need to replace everything. So the inner part of the pixel detector and the outer part with the strip detector. So we'll go from this geometry to the new one, which is on the right. So now we'll focus first of all on the inner tracker. There is also a dedicated poster by Antonio in the poster session. So here we have 3 different regions, essentially barrel 1, and then one forward region composed by 8 disks and another extended end cap with other 4 large disks. So the coverage also in this case will reach for the tracking up to eta equal to 4. And we will go as close as possible to the beam pipe with a distance of 2.75 centimeters for the first layer. So we essentially will build the inner detector with the pixel sensors, and we will have only 2 types of modules. One composed by 2 readout chip and one with 4 readout chip, and there will be about for 4,000 module and for total 2 billion pixel. So the readout chip will be the only active element on the module itself. Here there are just a SketchUp with components. And this is essentially just a picture of the first prototype. This is the R53A chip, which has been produced as test. Then the sensors. Here there is an intensive R&D program which has been carried out. There are some posters which essentially give all the details on what has been done and the result obtained. And actually, the baseline is composed by pixel sensor with a cell by 25 by 100 centimeter square. Micron is not centimeter square, obviously. They are micron square pixel cell with 150 active thickness. So we will have 2 different technologies, planar sensor with bit and implant and 3D sensor for the layer 1. This is mainly due to the better power consumption, because with planar sensor, first layer we'll have some problems with the cooling of the system. So we decided to go for the 3D pixel in the layer 1. The readout system, this is something I don't understand. The readout it's coming, okay. No, this is completely. Yeah.
Maybe you could take it off.
Okay. Sorry, I don't know if or not.
Okay, sorry.
So, okay. This is essentially a common project. So it's almost the same chip, the similar chip to the one presented and used by Atlas. So it's based on the RD53 project. There are some differences with the flavor for CMS. It's commonly named CROC. So the first buffer level test has been performed or are ongoing essentially, and there is a poster with the detail of all the setup and the first result for this kind of test. The main features are essentially the radiation tolerant up to quite high radiation and the possibility to provide power by serial powering via on-chip shunt LDO. And essentially for the CMS flavor, we will adopt a front-end linear architecture, an analog front-end linear architecture. Then this is the readout architecture. As I said, on the pixel module, there will be the only active part is the readout chip. So all the communication electronics are outside the module and are hosted by the so-called ports card with all the opto electronic and for the communication with the outside world, essentially. And so there will be this link, electrical link between the module and this port card, and then from this on the outside world, everything will be optical, and this essentially will perform all the control of the detector with 28 boards to control everything on the detector itself. Then the powering scheme, this is essentially an important feature in order to reduce the material budget inside the tracking volume. So everything will be essentially powered by giving constant current to a series of modules, and then thanks to this shunt LDO technology, the needed voltages will be regulated directly on module, and the chip on the module will be essentially in parallel. Mechanical structure here to decrease the material inside the volume of the detector. We'll go with carbon fiber structures where everything essentially has been minimized in order to avoid a huge use of material, and where all the routing of the fibers and cables have been optimized in order to be in the safer position with respect to the radiation. And the cooling will use the evaporative CO2 system in order to have, also in this case, quite small cooling pipes and less material. So now going to the outer tracker, so to the outer part of the detector. Here also we can divide the detector in 3 regions. Then I will specify what we mean with PS modules and QS modules. Here we have 2 barrel parts with 2 different technologies, and then the disk on the end cap. Here with the outer part only, we'll reach the tracking up to 2.5 HITA. And we'll use 2 different types of technologies, as I said, microstrips and macropixels in this case. And here the barrel geometry for the inner part, we change it from flat to a tilted geometry to optimize the number of modules and also the performances of the detector itself. So what is the main point of this detector? That we want to use track information at level 1 trigger. So we want to essentially get data at 40 megahertz directly from detector in order to be used in the level 1 trigger itself. So we need to reduce somehow to filter the number of hits that we get from this module. And to do this, we need to filter in PT essentially. So we need to build some modules which essentially can can cut particle with low PT directly on the module itself. And to do this, what essentially the solution that we found is to build module made by 2 silicon sensors, which are with a small spacing, and then correlate the information from one module to the other. This means that we need to read out the 2 sensors with the same essentially chip with the same readout system. Then the information from this we can cut, changing the correlation windows between the 2 sensors, the cluster in the 2 sensors, and we can create the so-called stubs, which then can go at 40 megahertz directly to the track trigger, and we can build track to essentially add this information to the trigger itself. These are the 2 kind of module, as I said. There are 2 types, one made by 2 microstrip silicon sensors. The sensors are made by 2 columns of strips, which are completely independent, so one on this side and one on this side, and they are read out on the 2 sides. The other type is made by a microstrip sensor and a macropixel sensor. For macropixel, we mean sensor made by 1.5 millimeter by 100 micron pixel. So here, just a picture of the first prototypes that have been built this year with almost the final chips and hybrids. This is a 2S module, and this is a PS module. Now it's time essentially to test, beam test in labs, irradiation and stuff like this in order to prove that everything is working and then go for the pre-production and then production. This is just an exploded view of the modules to show all the components. This is just quite complex system to build and to get it working. Here are all the components that are on the chip. There are essentially the readout chip and then the service which are directly on module, so low power GBT and VTRX Plus and DC-DC converters. Each module is completely independent in terms of powering and communication with the external world. The readout, we have essentially 3 chips for the readout. The first one, which is the so-called CBC, CMS binary chip. There is also a dedicated poster to describe the technologies used in this case. It read out the 2S modules, so the strip sensors. Here there is the chip, and thanks to the flex hybrid, we can essentially connect both sensors, the top one and the bottom one, to the same chip. While for the PS system, we have 2 kinds of chip. One, the SSA, which read out the strip part, and the MPA, which is the readout chip for the pixel detector. All the operation, in this case, for the stub creation and correlation between the sensors are essentially done on the MPA itself. Then on each module, there is also a concentrator, which essentially is the data hub to the external world. Backend of the system, so here are the communication of the module with the outside world, with the DT data trigger and control system. Here also there is a poster which describes the first readout system based on the Serenity board. And we have essentially communication about 2 gigabit from the DTC to the module, and 2 flavors of 5 and 10 gigabit to the module to the DTC for the data for the level 1 and the DAC, the readout essentially of the data itself. So the system is synced to essentially have a flux of data for the level 1 trigger of 40 megahertz, and then after the level 1, the data will essentially come out, the full data will come out at 750 kilohertz. Powering, in this case, will be a complete parallel powering with a single, essentially, power system which provide low voltage and high voltages. Then the conversion with the needed voltages are essentially done on the module itself, thanks to the DC-DC converter. And also in this case, the cooling is based on the 2-phase CO2 system. Material budget, this is the most important result. So this is the reduction that we have from the actual tracker to the the phase 2 trackers in terms of radiation length of the material inside the tracker. Just to conclude, just a couple of snapshots of the performance, the expected performances. So here we have the track reconstruction in terms of resolution in PT and resolution in impact parameters. So you can see that we improve and extend essentially the performances of the actual tracker. While here we have the tracking efficiency and the fake rate that we expect for different pile-up condition. Here there are, this is really a yearly simulation, which we understand that we have a problem in this point, and with the optimization of the layer distance, we avoid this dip at eta almost 1.2. So I come to conclusion. So we have this really ambitious project underway for the CMS outer tracker and inner tracker, actually. So the design is think to at least maintain, but also improve the tracking performance compared to the actual detector. And one of the most important point is include the track reconstruction directly on the level 1 triggered primitives at 40 megahertz. Actually, we have essentially starting to have the final prototypes for the outer tracker and the first C-Rock chip for the inner part. So the system are now essentially performing all the tests necessary to start then the pre-production, which will happen essentially the start of next year, and then go in production in order to be ready for the start of the high luminosity phase. Thank you.
Thank you, Alessandro. Are there questions? Maybe I take one while we wait. But did you decide which type of sensor to use in the pixel innermost layer? So 3D of planar?
3D for the innermost layer, for the 3D, for mainly for power consumption reason. Because after all the radiation, everything will go up.
Okay, that's as Atlas has shown. And the other difference I notice is that you use the rectangular shape in the pixel detector everywhere.
Yep.
So did you study differences with the square instead?
Yeah. I mean,
I don't think you showed any.
No, this is not here. It's just a review with not so much details, but there is all the studies that we carried out, at least in the last at least 1 year, with all different geometries. The squared one, the rectangular, and also the bricked one has been simulated, and then in order to check the performances, at the end it come out that the best compromise in terms of performances and the most simple way to read out and to build everything is to have the rectangular one, which gives us the best results and the simple construction of the module, everything.
I take this mic. Did you test the idea of the stub?
Sure.
On beam and efficiency?
Yeah. There are actually with the final module there are many test beam which are ongoing. Then there have been with just demonstrator. This is some times ago with mini sensor and just two readout chips. All the tests that has been done.
That with 2 readout chips.
But I mean the result are we are analyzing also the full modules now. Okay. We are not ready for this conference, but there have been many beam tests now with everything, with all the full module itself.
More questions? No.
Okay, thank you again,
you.
Alessandro, for the nice overview. Is Gianluca for Alice perspective, long term. Let's see if we can.
Corretto? Test. Okay. Thank you. Good morning. It's my pleasure to describe the ALICE ITS3 project and its goals. Here is the outline of my presentation. It will be an introduction to the ITS3 project and second part on the developments of the sensor. And then I'll try to give some insight on one of the prototype chips that we are designing towards this application. So the starting point is the current inner tracker of ALICE. It's called ITS2. It's a 7 layers detector for a 10 square meter of sensitive area built with more than 24,000 pixel sensor chips, monolithic pixel sensor, which are called the PIsa chip. It's a 12.5 gigapixel camera, this object. And just to be on the same page, monolithic pixels are devices which have pixels and readout all in one silicon die. Let's look at the 3 innermost layers. This is called inner barrel, and the concept of the ITS3 project, the idea of the ITS3 project is actually to replace these 3 innermost layers with a new detector in which flexible printed circuits, cooling, and services and mechanical structures are removed, and the sensor is the only thing that you have in the active area. So we'll see how we try to do that. The main change would be a significant reduction in material budget. The radiation length would go down to 0.05% of radiation length. And also there's a second parameter changing the radial distance from the beam, which goes from 22 millimeters down to 18 millimeters. With these changes, there is an enhancement in the tracking and vertexing performance. The pointing resolution has an improvement of factor 2 over all momenta. The tracking efficiency is largely improved, especially in the low transverse momentum regime, which is where the ALICE research program focuses. So let's discuss a little more on the layout and some general requirements of this new detector. So it will be built as 3 true cylindrical layers in 2 halves, so half cylinders if you want. These have to be made with large wafer scale, dimension, single dies, so which will be curved and bent. So the technology is monolithic active pixel sensors. The length of these devices should be as large as 27 centimeter. It is needed to thin down these devices to 50 micron. That's the only way you can then bend the device, actually. The position resolution for the sensor is required to be about 5 micron, which calls for pixel pitch of the order of 20 micron. For some more words on the electromechanical integration, there is, as I said, already no circuits in the active area. At least that's our aim and hope. So there is a need to distribute the power supply and transfer the data along the chip itself, all in the metal stack of the CMOS device. And the cooling has to be by airflow to further reduce, to achieve this low material budget. So we need to dissipate less than 20 milliwatts square centimeter on the full chip. And here is the pointer to the LOI where the project is described in more detail. But can a bent sensor actually work? We believe so. This has been demonstrated with the PIsa chip, so with the current sensor which we use in the ALICE ITS2. Here is the first publication on that. The chip is here, is bent at the radius of 18 millimeter. And the plot here is quite unusual. It's the inefficiency, actually, of tracking. So the lower here is the better, and the lines are 99.99%, 99.9%. And the color here are different sets of rows which correspond in such a setup to different incidence angle of the particle. So, and this is very well in line with our expectations. In short, there is a comfortable operating range for such a device even when it is bent. And in the project, we are gathering quite some experience in operating and running bent devices. Here is a setup in which there are 6 chips bent at the radii of the ITS3. And over the year, we expect to have results from these tests being published. The other big question is, can one make such a device, 27 centimeters times 10 centimeters for the for the outermost layer? bent, and this is actually proven here. This is a prototype, a mechanical integration prototype, which is made with 3 dummy silicon layers. The layers are thinned down to less than 50 micron, and all held in place by very lightweight carbon foam supports. So the question for the sensor development, for the microelectronics development, is actually, can we make this structure with true functional pixel detectors, monolithic pixel detectors, and replace the dummy objects with functioning one. So we need to do quite some aggressive development to aim for this dream. And this is made by a series of submissions in silicon. Here are sketched on the timeline of the project, which aims at install this new detector during long shutdown 3. The target technology is it's a 65 nanometer CMOS imaging technology. It's Tower Jats Panasonic is not the one which the pixel chips, for example, that we have just seen are built. This technology is implemented on 30 centimeter wafers, and it provides the stitching technology. I will explain a little more on this, which is what enables to build such a large device. The first submission, MLR1, has been made, and I will present just some key items from this. We are currently working to complete the second submission. The design activities of the microelectronics are actually framed into the CERN EP R&D work package, which actually has been quite successful to share and coordinate microelectronic design effort across several teams and people of many institutes inside and outside the ALICE collaboration. So the first submission, the MLR1, this was completed in December 2020. Now we have chips being tested. The primary goal of this submission was actually to learn about this technology and to see if one could make detectors with that, and also to characterize the performance of the devices. This submission contained a number of prototype circuits, very simple structures, but also functional blocks and pixel arrays. Most of them implemented in common small test chips, 1.5 millimeter times 1.5 millimeter. You see here a full detail of the large variety of structures which were in this submission, and the photograph of a quarter of the wafer. So I'll try to give some key learnings from this first submission. The transistor test structures, they are working as expected. They've been characterized, and they are quite similar. They present a similar performance to the other 65 nanometer technologies that have been characterized for high energy physics. The submission also contained building blocks, which are now proven in silicon, so we can reuse the circuits for the next circuit design. These have analog functions, bandgap, DAX, temperature sensor, VCO. It contains also pixel prototypes, and we see here 3 examples, the APTS, DPTS, C65, with matrices of pixels of different pitches, different sides, and different readout schemes. So this is actually providing a tool to have quite a detailed characterization of these pixel arrays, and this is currently ongoing. The first submission also allowed to test some process optimization, which were useful to increase the margins on sensing performance, which were actually developed on the previous generation, the 180 nanometer technology, and this is also proved to be working and actually quite useful with the new technology. I'll give a selected example. Here is the results of a beam test with one of these pixel test structure, the digital pixel test structure. The 2 of these devices are put in a telescope in which there are other 6 layers made by the Alpide chip. And the key results shown here is that we achieve the detection efficiency larger than 99.5%. This is extracted by indeed checking the tracks that are seen by the telescope and their presence in the 2 devices under test. This is not only one beam test, now this has been repeated, so it's quite a comfortable result which has been demonstrated. And let's move on to now more on the microelectronics. I need to give a little introduction to the stitching. A microelectronic design is based on producing a file which it's a design reticle. Okay, you give to a foundry which will produce the devices. And normally these are areas of 2 times 3 centimeter, which is the limit typically of a large components or device that one can make. Now, the stitching is a technology which allows to, by precise alignment of the image which is shot over the wafers during the photolithographic processing, to actually make a device, a circuit, which is larger than the reticle. This is made by dividing the reticle in some frames, and at production, some of these frames are repeated in arrays, so essentially you can build something which is a multiple of the design reticle and have this degree of freedom. The next silicon submission then is called ER1 and has as a main aim to learn and prove the stitching. It contains two large stitched sensor chips, the MOS-S and MOS-T. They explore some different approaches to the key question here, which is the yield in building such a large device. Here I'm showing the floor plan of the 30 centimeter wafer, which will contain these circuits in which the MOS-S chip is this slice here and in the red rectangle, and the MOS-T is a thinner object, which was also put in evidence there. The submission will also contain additional test chips. We continue the development of the Pixel, as well as building blocks like the prototypes for the fast serial links. The MOS-S is the one of the prototypes for the stitched sensor. The primary goal of this design is indeed to learn the stitching technique to make a particle detector, to explore how to make the interconnects of signal and power on a wafer scale chip, to learn about the yield that we will obtain from that, and to study also power leakage and other electrical parameters of the circuits. How it is made, we design one repeated sensor unit, which looks like one chip, and this unit is repeated 10 times. It's completed with some end caps, and the stitching technology is actually used here to make metal stripes to distribute the power across the full structure, and also to provide some long-range on-chip interconnect buses for data transfer. The layout of the chip is shown here, so we will have an object which is 14 millimeters in this dimension here, times almost 26 centimeter, containing 6.7 megapixels. If we look into one of these repeated units, we would see that it contains 8 matrices with 2 different pixel pitches, one large or coarser 22.5 micron and one finer. So this corresponding to different densities of the circuits that we implement on the chip. So the architecture of the chip has these 4 matrices with a dedicated independent analog distributed circuitry, a region readout, and then a top-level readout and control. And this is quite canonical. It's important to notice that we have this segmentation in parallel units, and the chip contains this stitched communication backbone, which allows to transfer the data across all the repeated units, across the stitching boundary towards the end cap, where we can have control and prototype and test the readout from one short edge only, in addition to the more canonical control and readout to the long edge. So the chip will provide different testing scenarios. Here are some examples. We would start with testing the units independently, powering each of one independently from the others, and see how many of these are operational. So the primary question is indeed what is the manufacturing yield for each of these units, and that's why we made such a granular architecture. We want to study that yield at the half unit granularity, at the block level granularity, and down to the pixel level granularity, and essentially study if there is a possible dependence on the density of the circuits, which is what I mentioned before related to the pixel pitch. So come to the summary. Described and the aim of the ALICE ITS3 project, which is to replace the 3 inner layers of the ITS2 with wafer scale bent monolithic pixel sensors. As of today, I think we believe that we have a proven operation of thin sensor bent at 18 millimeter radius. So that's at least with the 180 nanometer technology proven. A full-scale mechanical prototype has been built in the project, and we are doing the developments towards the sensor. The technology has been validated for particle sensing. Detailed characterization of the prototypes of the first submission is currently ongoing, and we are now trying to complete the ER1 submission, which is our next step to learn the stitching. And I described one of the stitcher prototype, the MOSS chip, which is a 14 millimeters times 26 centimeter stitch sensor chip, which aims at providing a platform to study experimentally the yield, and prototype power and signal distribution, and actually study quite some large pixel arrays. So the ALICE ITS3 project is quite happy to be pioneering such a large area maps sensors and their bending. We see that this is sparking the interest of many groups for other experiments and applications. We're certainly very happy of that and very open to proposal for collaborations and interest. Thank you very much.
Thank you, Gianluca. Beautiful project, I would
Thank you.
say. Oh, there are several questions now. I don't know who was first. Norbert here.
Thank you also for this very nice presentation of the interesting project. Can you say whether you observed anything that is due to the particular stress that the structures and the chips have? Did you observe anything that behaves differently compared to a planar sensor?
Yes, I don't have a slide here, but indeed the Alpida chip shows a different current consumption with the bending, with the stress, really proportional on it, repeatable. So this has been studied and we have data on this. So the effect was that we need to tune a little and compensate the setting of the thresholds, for example, or Daxen biasing. But apart from that, the performance is then maintained. So we don't observe major things, but indeed there are hints on the effects of the stress on the circuit. And we need to study that on the 65 nanometer technology. That's one of the questions I had indeed.
And regarding the stitching, that does not suffer from the bending? Or did you not test the stitching with bends?
We don't have yet a stitched prototype. There are plans to study bending of large area devices using the MLR1 reticle, so the same technology, but yet not a design which is full wafer scale. There are one here and one there. So.
Yeah, so there are several questions. Okay, one over there.
Hi, thank you for the talk. My question is similar to the previous one. Have you tried using your demonstrator to do any kind of thermal cycling to see whether having a bent sensor under thermal stress is likely to work or not?
Well, actually, these devices have been stressed quite much in preparing this device, and we are ourselves surprised that they actually have very repeatable performance. So about thermal cycling specifically, I don't recall as of now, but generally this is not one test that was made. These devices have been really routinely bent and re-powered, retested, and that as of now, we don't see any degradation of this Alpida chip after this repeated bending. Maybe
Sorry, there was first that colleague over there.
Hey, thanks for the nice talk. Were there also tests of like bending to smaller radii than 18 millimeters?
Not with functional, not that I am aware, I have to say. Probably yes, I'm not involved directly in that part, but I have no data on testing it at lower radii. I think it was tested, and they do not break, so it goes to lower radii, but I have no data with tests on those structures.
Thanks.
Roland Horisberger. Could you say a few things about the readout architecture you're planning to implement into the pixels and the overall readout scheme, and what type of data rates, hits per square centimeter and second, do you plan to deal with this type of readout architecture?
Okay, so can we get back to the slides, please? So the flux of particles is 2.2 megasquare centimeters. That's an environment certainly less demanding than the high luminosity environment for Atlas and CMS, with a LED interaction rate of 50 kilohertz. The architectures, we actually, on this prototype, have not yet focused our efforts on the readout architecture itself. The moment we are rebuilding from existing know-how, which is a readout similar to the Elgats chip, but we are also exploring with the other stitched sensor an asynchronous transfer of discriminated pulses from the matrix to the periphery. So we have two approaches: a strobed latch of the discriminated signals, which are discriminated in pixel, and then transfer to the periphery and then to the end cap. Or we're going to look into transferring the discriminated pulse immediately, so data-driven push to the periphery, where then this data would be sampled and transferred to the end cap. But as of today, we are focusing more on learning how to build a stitcher device rather than studying now the architecture. This is for year 2, the submission even after year 1.
Okay, I have a question which is related to the mechanical. First, it's great experience you are doing. And when you bend, how do you keep the accuracy of positioning of this object with respect to the rest of our values? That is...
I think there will be certain I'm not working on that. There's the work package on the mechanical integration, and I think these will be presented by the colleagues in other workshops. First of all, there has been already quite some development in how to make these interconnects of the carbon foams, structures, or pillars to the silicon. So this is not the first try, okay? You have to go through a development. Interestingly enough, then this has been, of course, characterized in terms of the accuracy by doing tomography of the structures and measuring. And there are even effects of the stress induced by the gluing that one has to take into account. So indeed, all these things are part of a development process in a dedicated work package where this is being accurately studied. So we seems to have at the moment an overall feasible path to a proper uncertainty in the final positioning. Then, in theory, I think for the relative alignment of all the structures, since you have now a monolithic die, once you know where it is, all the rest it comes together. So you don't have the usual problem of finding every chips where it is and compensate. But okay, sorry, I'm not maybe able to.
Well, but that's interesting enough. Thank you.
Thank you.
Let's thank you again, the speaker. You will tell me the time. Huh? Okay, so now we have a change of program. So before the coffee break, we will show you a summary of the posters that you will have a chance to see during the coffee break. Indeed, we have received a lot of posters. You see here 47 showing the large interest in the field. And we decided to divide them, as you see here, between the current development or detector in construction and then R&D, short-term or longer-term. Of course, I mean, you will see there is a lot of interest in precise timing, as we already got the message this morning. Our summary is presented by dividing this large amount of poster in macro areas, and for each of them we try to go from the current construction activity to short and long-term perspective. As you see from the statistics, the newer are the technologies, the more are the short and long-term number of posters presented. So I start with the system overview. So we have Christian reporting about the Bell 2 vertex detector. He is reporting about the performance of this detector, in particular reporting efficiency and the monitoring of the damage from radiation. Then we have a nice poster by Gianluca about the Velo upgrade and its construction and just being successfully installed just in time. And then something slightly different about the monitoring of the data coming out of the detector that, in the incoming run by Luca, monitoring, so developing machine learning algorithm for the analysis of the data quality of the pixel detector in CMS. And then there is a poster by Paolo on the performance of the pixelated timing detector in a MEG2 upgrade. This instead is a report about a data taking that is passed. So it will report in particular about time resolution and the problem observed in the performance, and will highlight some mitigation of these problems. Then looking to the forward detectors in Atlas and CMS, Maciej and Eduardo are reporting about the Atlas AFP detector and the CMS PPS, where we have different type of detectors. So for Atlas, it's a combination of a silicon tracker and time of flight, and Maciej will report about the current status and also some highlights for the upgrades for iLumi, while for the PPS we have diamond detectors, and here Eduardo will report about the status of the art. Now looking forward, Antonio will present a poster on the preparation of the pixel detector for iLumi and all the challenges we heard also this morning in the talk. Susanne, for the Atlas tracker update instead, she will, in her poster, she reports about the interlock system, so this is across the full tracker, and she will report about this hardware protection system based on a FPGA interlock matrix and how to protect the detector in operation. And then we have two talks, two posters for the performance. So Marianna is reporting for the Atlas tracker the performance of, let's say, high-level objects like B-tagging, pile-up jet rejection, and also photon efficiency. And we have another one by Ludovico about the possible expected improvements in the performance of the Bell 2 with an upgrade of the pixel detector with monolithic pixels. Now, moving instead on the pixel technologies, pixel detector technologies, here we start with Rudy, that is showing the performance of 3D and planar pixel detector produced by FBK in view of for the CMS detector. And also Clara presents a talk for 3D pixel performance from CNM, again with the focus of the upgrade of the CMS detector. Both are focusing on the performance after strong irradiation as they need to do for the iLumi environment. And then always for CMS, Franz presents a characterization of passive CMOS sensor after strong irradiation. So this is a pretty, let's say, interesting technologies that CMS may deploy for the upgrade in this round for iLumi. Moving to Atlas, here we have a set of presentation more focusing instead on modules and demonstrators. So Habi has prepared a poster to explain how the collaboration is preparing for producing a large number of modules, how to assemble them, the structure of quad modules that Laura presented in the talk. And then we have a couple of talks on the demonstrator. Nicola is presenting how the setup for the outer barrel is monitored through sensor and interlocks. And John will instead present the different setup demonstrators for the different subsystem of the pixel detector. So the end caps, the inner system, and the outer barrel, in particular reporting about the performance in serial powering. And then looking a little bit forward for future detector beyond Illumi, we have Chiara presenting the performance of in time resolution for 3D diamond pixel detector, and Matthew presenting 3D silicon sensor with, you see, innovative pixel shapes. And Efren as well is presenting performance of single cell 3D in lab and test beam, and it will show the current achievement in time resolution. Now moving to strip detectors, here, so this part is dominated by Atlas silicon performance, because Atlas is already in production, so there are a lot of, or some poster about quality assurance measurement. So Xavier, for example, will present the analysis of the humidity sensitivity of the strip sensor in pre and post irradiation. Then Giri is presenting or reporting about two posters. One is the characterization of the polysilicon resistors as a function of temperature, again pre and post irradiation, and also the effect pre and post irradiation of the resistance across the interstrip resistance. And then David is reporting how we manage to retrieve all this data from the quality checks and store them and analyzing through this distributed production. Punit instead moves a step forward and will report us about the performance of the modules on the staves, how they behave. You see, for example, plots of the noise along the staves in cold and warm temperature. And the last talk of the poster of the strip is instead from the foot collaboration, and Gianluca will report about the performance of this small silicon strip telescope for this experiment that is target to measure the double differential cross-section for nuclear interaction for interest of hadron therapy. Okay, now we move to you. Okay. Jerome.
Wait. Better, sorry. Thank you. So, indeed, let's continue with posters related to the MAPS technology. And again, we start with the system that Gianluca introduced and that Hartmut is presenting here on the commissioning of these 10 square meter, which is the largest surface so far covered by such sensors in Alice. Then still, most of you might know this UDET telescope with which you are testing your detectors, and Leonard will tell us how to complement this telescope with high voltage CMOS to get time resolution in the telescope there with some nice results. Then slightly with different flavor, the Malta monolithic CMOS pixels will be presented by Heinz, and especially results, latest results on version 2 of Malta with the radiation tolerance up to a few tenths to the 15 neutron equivalent per centimeter squared, along with a nice time resolution obtained. Still with Malta, Florian will explain you how you can build interesting modules, of course super light, with Malta or Malta 2, and a number of sensors aligned here, as you can see. Moving forward, still with systems built from maps, as we've been introduced yesterday morning about the EIC project. Giacomo will tell us about how to foresee a system for this future detector based on maps, essentially for the vertexing and tracking with a very light material budget. And again, based on the sensors that Gianluca introduced to us a few minutes ago. And I think this is the last poster in the map session with something slightly different from colliders. And here, Muliri will tell us about a pixel chamber, which is basically like a nuclear emulsion, where you pack all those sensors and are able to basically track in 3D or image very the decay of typically charm and beauty directly. Okay. So I forgot that we also. Yeah, we have still a few more, sorry. So further away, maps is really popular, you know. So here again, we are back in more developments, again with the high voltage maps here. And Horacio will tell us about this development to reach even further radiation and especially high dynamic to monitor, detect very highly ionizing particles, as you can see here. Then we will be discussed by Coralie about the Arcadia project with fully depleted maps in specific technology, allowing to reach, although quite interesting time resolution, as you can see here. And, whoops, moving too fast. Then again, changing technology, and this is Finn, who will tell us about development in 65 nanometer technology, so the same that the Alice ITS3 project is using to develop a new kind of maps for future applications like lepton colliders and X-Factory. So this will be essentially about both simulations and testing of the designed prototype. And then we will move still to another technology, silicon germanium BCMOS process, where the monolithic project discussed by Matteo will tell us how you could hope to reach few, few picosecond, here 20 picosecond resolution with fine grain granularity pixels. That is now really closing the maps session, and now we have also a few posters on low gain avalanche detectors. First poster reviewing actually what is available and what could be new developments in this technology by Paternoster here, where I mean the concept is discussed, especially here as you see with trench type Elgat, and how they could resist extreme fluences. Then an application to these Elgat sensors to the Pioneer experiments, which will be discussed by Jennifer here, with the explanation of what is the goal of the experiment and how Elgat can help here. Then we will get Croci discussing the simulation of innovative Elgat devices targeting to reach this dreamed 4 dimensions, so 3 position dimensions and 1 time dimension, of course, tracking, which will help actually have a very efficient tracking in a very, very dense environment. So this is essentially about simulation, as I said before. Then again, we will know from Marta about machine learning techniques with resistive readout type Elgat to combine the well-known excellent time resolution with also excellent position resolution with such device. So also going into the direction of 4D tracking, I would say. Now, for the rest of the posters, this is a mix of various technologies, again, going from things that are, let's say, currently in production or in use to more future prospects. So Alice will tell us about the response of diamond detectors, which are routinely used to control radiation in various environments. So the response of such diamond detectors to high energy electron pulses. Then we'll move to something completely different from diamond, but still, well, semiconductor, which are skipper CCDs, which is completely to the fast timing, super slow detector integrating over a long time, but with extremely low noise, and so extremely useful for typically dark matter search. And Brenda will tell us about that in a poster. Then we will move to silicon drift detectors by Cirincione here. Explaining us how a system reading many such, well, a number of such detectors can be used, in fact, to, sorry, I forgot, yes, to combine the nice energy resolutions that such detectors can provide, as you see here. Still on SDD, we'll get Nava discussing high rate and high resolution SDD for another type of application, which is electron microscopy, which will be interesting neutrino physics through the Catherine experiment. And then we'll have 2 posters with silicon photo avalanche detectors. You know this is a basic element from CPM. So first we'll get Gianmarco discussing SPAD in CMOS process to detect charged particle and trying to reduce the dark count by combining 2 devices. Then again about minimum ionizing particle detection with not SPADs in, well, you see, yes, SPAD in CMOS technology again. And this will be Emanuele discussing this with an arrangement to do the tests for the time resolution. Then in future device, which could be based on negative capacitance ferroelectric devices, we'll get Daniele discussing what could be the performance of such devices under radiation from X-ray. So trying to simulate through TCAD modeling the behavior of such detectors. And then Asuras here will discuss P-type silicon MOS various devices and how they sustain irradiation from X-rays from a cobalt source. This is targeting also ILUMI LHC application and trying to model those behaviors with TCAD simulations. And I think that was the last poster. So we're done with this numerous contributions, and we invite now you to have a look at them during the coffee break. And we reconvene at 10:30? 35. Well, we got 5 minutes. Thank you very much.